Climate change is resulting in unanticipated negative impacts to the planet and humans. The goal of this presentation is to highlight new scientific information demonstrating that climate change is disrupting key parts of the global carbon cycle, specifically relating to oceans and the Arctic. This is a global carbon cycle. The blue numbers represent pools of carbon, the red numbers represent fluxes of carbon. My talk will focus on the oceans and Arctic soils because they represent the largest pools of carbon and are increasingly being affected by climate change. The ocean covers 70% of the planet and stores 38 trillion tons of carbon. Arctic soils cover 25% of the northern hemisphere landmass and store 950 billion tons of carbon. So how is climate change disrupting carbon cycles in the ocean and in Arctic soils? Oceans are absorbing carbon dioxide from the atmosphere. This is good in some ways because it reduces the greenhouse gas effect in the atmosphere. But more carbon dioxide in the ocean leads to higher acidity, which harms marine life upon which human livelihoods depend on. But new scientific evidence has emerged to show that ocean uptake of carbon dioxide is slowing. Now, this is not to suggest that marine life will not continue to be harmed, because the ocean will still uptake carbon. However, this slowing of oceanic carbon uptake will result in more carbon dioxide staying in the atmosphere, increasing the greenhouse gas effect and accelerating climate change. This is information that was not included in previous IPCC reports, because our understanding of these sinks is still evolving. But what we do know for sure is that these carbon cycle feedbacks will have significant and irreversible impacts. This graph demonstrates the slowing of carbon dioxide uptake in the ocean, resulting in increasing carbon dioxide in the atmosphere. Please note that 40 years ago, 40% of carbon emissions stemming from the burning of fossil fuels remained in the atmosphere. The remaining 60% was taken up by land and ocean sinks. Today, almost 50% of carbon emissions are remaining in the atmosphere because the ocean is no longer absorbing as much carbon. Now, switching gears to another large pool and increasing source of carbon, the Arctic. Arctic soils are thawing. The impact of thawing Arctic soils is increased methane emissions. It is important to note that methane is 23 times more potent as a greenhouse gas than carbon dioxide. These methane emissions have largely been an unanticipated and therefore understudied source of carbon emissions. This graph and map shows the area of permafrosted soil is decreasing and is expected to decline further. The dark blue area depicted in the map on the right demonstrates the dramatically smaller area of permafrosted soil projected for 2100. To give you a sense of the methane emissions from thawing permafrost, it's expected that in 2025, which is where the red arrow is pointing, 10% melting could result in methane emissions that would lead to a 0.7 degrees Celsius increase in temperature. Now, that's only 10% melt, but these scenarios demonstrate that within 100 years, the consequences could be far worse. Now, I'm showing this map simply to illustrate that while permafrost thaw has serious implications as an increasing and accelerating source of carbon emissions, there are also other important pools of stored carbon that will be released as climate change intensifies and accelerates. Most of these other pools of stored carbon are at the mercy of extreme weather events, which will invariably increase with climate change. So in conclusion, ocean uptake of carbon is slowing. Thawing Arctic soils are releasing stored carbon, and therefore more carbon is staying in the atmosphere. These impacts will accelerate and reinforce these feedback mechanisms, resulting in catastrophic and irreversible impacts to states most vulnerable to climate change. For this reason, the 350 ppm target is not enough.
Now, as Henry mentioned, the melting of glaciers and permafrost is contributing to the release of methane, but it is also contributing a large part to sea level rise. This is particularly important because it means that the IPCC fourth assessment report projections are severely underestimated, since they don't take into account this additional contribution of the rapidly melting ice sheets of Greenland and West Antarctica. This point is further illustrated in this graph here, which is part of the Climate Congress synthesis report that Professor Lee mentioned earlier. The shaded gray cone represents all of the different IPCC projections, including the upper and lower bounds of their uncertainty estimations. However, the squiggly blue line up top actually details the actual observations of sea level rise relative to 1990 levels, which has been about 3.3 millimeters on average per year between 1993 and 2006. This is in direct contrast to the IPCC projections, which are based on an average of 2 millimeters per year through the course of the next century. So this really means that we are well on our way to greatly exceeding the maximum 0.6 meter sea level rise that the IPCC projected by the end of the century. Using the actual observations, we can project a half meter to a 1.4 meter rise, meaning we could easily have 1 meter or more rise by the end of the century if greenhouse gas emissions do not peak very, very soon. We are already committed to at least some increase in sea levels due to continued warming from greenhouse gas concentrations that are currently in the atmosphere. But the key is to act now to prevent reaching the higher limits of the 1.4 meter projection and hopefully keep the increase closer to the half meter low limit. However, even with a half meter or more likely 1 meter sea level rise, there will be dire consequences for small island states, some of whom will certainly lose all of their territory. You will have the details of this chart in the materials that we're going to hand out at the end, I believe. So don't worry too much about the details presented here. But if I can direct your attention to the red boxes, which is the percent of total land area under 1 meter of these 8 island states, they're a representative sample. You'll notice that islands like the Maldives and Tuvalu are very low lying, and 80% of their land area lies below 1 meter, meaning that they would be almost entirely wiped out by the end of the century. Another concern is that small islands also have some of the highest population densities in the world, and that most of the people on these islands live close to the shores, which are exactly the areas that will soon be underwater. On more mountainous islands, such as Grenada, St. Lucia, St. Vincent, and Dominica, closer to 90% live near the shores with limited opportunities for inland migration should the sea levels inundate their coastal communities. But the most important message, perhaps, is that we are already seeing impacts of sea level rise on human populations. For Tuvalu is a good example that gets used all the time, but Papua New Guinea has actually already evacuated some of their islands, and Kiribati has evacuated some coastal people inland on their islands. All right. Now, an issue that is not often considered when talking about sea level rise impacts is that it affects the size of a country's exclusive economic zone, since these zones are measured from the low water mark, and which would slowly creep up with ocean rise. So as the sea level rises, so the low water mark also rises. Now, there are several important implications of this, one of which is illustrated here. So here we have an island nation. This is one nation that's made up of several islands. And here are their associated exclusive economic zones, measured 200 nautical miles from the shoreline. They encompass, and these exclusive economic zones encompass important resources such as fisheries and oil and gas deposits. Should one of these islands become inundated by sea level rise and disappear, its related exclusive economic zone will also disappear, along with that nation's access to the resources that are encompassed within it. The same is also true of islands which consist of island nations that consist of only one island. As they lose their terrestrial territory, the outer limits of their exclusive economic zone will also shrink in. And another issue beyond rights to resources is the potential change of previously settled maritime boundaries. So now we have 2 different island nations, and should an island shrink in area, its exclusive economic zone will also shrink, leaving areas in the ocean completely open for other countries to exploit. Now finally, as a negotiating strategy during the climate talks, it might make sense to discuss these issues of sea level rise with the 8 developed countries, including that are up here, including the UK, US, France, the Netherlands, Australia, New Zealand, Denmark, and Norway, that have some 60 dependent and overseas island territories in the Atlantic, Indian, and Southern Pacific Oceans. Many of their overseas territories rely on tourism for generating revenue or serve as important military bases. But their ecological features are similar to the small island developing states that were pictured in the chart before, and they all share the same kinds of problems of sea level rise. Such as this coastal resort in Turks and Caicos, which is a territory of the UK, which could soon find itself underwater as well. In conclusion, though we should be most concerned with the effects of sea level rise on the most vulnerable states, we all, developing and developed alike, have the same interest in order to keep these islands viable.